Hi, I am Jason Martinez and I'll be presenting the part 2 of the Create Logical Database Design. So before I go into deep to my presentation, I would like to present the ER diagram presented by Miss Amami. So here it is. We have the student, the course, the instructor, seat number, class, section, professor as the entities of the ER diagram. So how are we going to convert it into a table? So here is how it goes. So we have this student table that has the following: student ID, student name, student address with the corresponding example. For the course table, course name, course number, and the corresponding example. For the instructor table, instructor number, instructor name, instructor faculty, and the corresponding example. Seat table, if we have the seat number, seat position, and the corresponding example. Another is the class table, course name, section number, registered, class date and time, and the corresponding example. For the section table, we have the section number and the corresponding example. And lastly is the professor table, which has the following: the professor ID, professor name, and professor faculty with the corresponding example. So this will be my basis on the next topic that I'm going to discuss, which is the augmenting the initial logical database structure with additional database objects. So let's first have this: the logical database structures can be refined by introducing supplementary database objects that might be required to accommodate the specific design requirements, such as different application reference code tables or artificial keys. But we have some of the example that I want to present to you. First example is you might need to create additional tables or columns for data journalizing needs, such as the additional of date and time data as well as the user ID. And from our student table, that's we have student ID, student name, student address. We could consider to add the following: the date, the time, and the user ID. So the date corresponds to the date when the user processed the data, and also the time when the user processed the data. And the user ID address designates that the user that processed the data is the user ID number one. Another example is it might be the addition of various flags to indicate that the records in a table have been processed in some manner. So let's have again let's have this student enrollment table. So we have this student ID, student name, the date, the time, the user ID, and followed by the enrolled column. The enrolled column is the one that gives us, or that represents the flag, wherein the flag of 1 and 0. 1 indicates that it is enrolled, and 0 indicates that the student is not yet enrolled. So that is for the flag. Another example is you might consider adding special fields that contain summarized data. So the summarized data for this student enrollment table is represented by the date enrolled. The date enrolled can be used to summarize how many students are enrolled on the said date. Or we can have it in the query uh, to have a range of date to know whether there are a lot of students or not a lot of students are enrolled during that range of date. Next topic is the denormalization. But as discussed in earlier module, the normalization of the data model helps to eliminate the major difficulties that are associated with updating redundant information and helps to improve the integrity of the data that is stored in the database. So suppose this is an example of the normalized table, wherein we have this very large number of individual tables for a large database. So some of which might need to be joined together to satisfy specific cross-table queries. Just like for my example, which is the student table can be cross combined with the class table. So maybe this is uh, the composition, that student table with the class table for cross table queries. And sometimes it will produce, if we don't have a good practice of cross-referencing of a table, we could produce a high performance of the CPU that will lead to uh, shutting down of our computer. So let's have this some of the considerations. First is the derived data. So entails is in storing in the database specific data that can be produced from other data, such as the derived field. For instance, total invoice. So let's have this example payment table that has this payment amount with corresponding value 10,000 and 15,000. So the derived data will be presented on the student enrollment table, where we can place the total payment so that we don't need to have another query on combining the payment table or getting the sum of from the payment table, then presented it into the student enrollment table. So here in the student enrollment table, we can easily get the total payment amount that the student already paid for this semester. Another example is, another consideration is the duplicated data. Sometimes you might need to duplicate some specific data from one table to another to improve performance. So let's have this student table as an example, and we presented the duplicate data, which is the student ID and student name, on the student enrollment table. So that's the duplicate data. Next is, sometimes you might need to store various types of summary or historical data in the database to ensure a faster response time on certain queries. A typical example would be that very frequent access detailed data to calculate a sum. In such a context, it is recommended to storing computed values immediately when the data is created at a higher level in the database. So let's have this exact example payment table that we have this payment amount and there. So the summary is the total payment amount, which is presented in the student enrollment table, that is came from the sum of the payment amount. So we already have the normalization. Now we have this refining and analyzing the critical data access patterns. So the data access that we created during the analysis phase should be revisited and refined with up-to-date volumetric information. The detailed data access paths of the most critical online transactions should be carefully analyzed to ensure that the logical database structure can accommodate them. In case of a critical program, it its overall job turnaround might become critical, especially when the runtime of the batch program is constrained by limited time window. So several alternatives design might be available to improve the response time of the most critical system transactions. In some instances, the logical database structures might need to be modified to accommodate some specific system transactions, and associated data accesses that themselves might need to be redesigned to meet the stated response time objectives. Another is the database designer with the application developers and even the users if necessary should also revise the cardinality figures that were documented between relations shown in the entity relationship diagram. The critical factor often used to identify the most efficient data access design solution is estimating the number of rows to retrieve as a result of each call. Then the associated estimates for CPU time are often compared to identify the best design alternatives. So simply plotting the estimated number of IOs for each data access, analytical modeling software, tools provided by database or third-party vendors. So we have to use some of the tools to estimate the number of IOs for each data access analytical modeling software. So in some cases, a relative simple prototype may be required to issue SQL calls against real physical databases that contain realistic but artificial data in order to assess and evaluate the best design alternatives. So this means we have to use a dummy data with almost equivalent number of records so that we can ensure that our prototype will be realistic. And for very large databases, full-scale prototypes may be essential to obtain realistic estimates for program execution. So the overall estimate should be refined by taking into consideration the enterprise data archival policies that apply to information contained in the logical database structures. So how many years will production data be accessible online, and under which conditions will they be archived? So furthermore, the volume estimate should not only include average occurrences for each specific entity, but also the estimated minimum and maximum occurrences of an entity. So the revised data sizing estimates are used to verify the hardware disk space requirements that were forecasted during the analysis phase. So in some cases, you might also want to verify how often the maximum number of entity occurrences can be encountered while processing the application data. So obtaining this information might be imperative in order to handle unforeseen situations in large databases. For example, the database structure might be able to support the processing of an average number of entity occurrences, but can fail to adequately support the processing of a few occasional but very large number of entity occurrences stored in a given table. So that's it. It's it's better to refining and analyzing the critical data access patterns in order for us to forecast how much I/O we need, how much hardware we need, and how much memory we need. So ibig sabihin, we need to reanalyze and refine it to determine the hardware requirements of our database. That's it, and the next presentation is the physical database design.